cloud. All right, shall we get underway? So welcome everyone to the opening colloquium, the first colloquium of 2021, a year that we sure hope is going to be better than 2020. But we are continuing the virtual colloquium format for the rest of this semester anyway. And we have, if you look at the screen here, a pretty fun, interesting, diverse in many ways lineup. So we hope you're looking forward to it. Looking forward to having you here every week. One quick announcement, Peter Busick asks that those of you who are here for the class, the colloquium class, plan to stay, I think, a few minutes after for some organizational conversation with him. So please just hang on and I'll just keep the room open and I'll promote Peter to panelists and take it from there. And then before we get started, I think Minnie wanted to have a few words with everybody. So Minnie, the floor is yours.
Thank you, Ariel. I just wanted to take this opportunity here as the first colloquium of the semester to welcome everybody back to spring 2021 and hope your semester is off to a great start. And just a brief announcement that next week we will have our first monthly community conversation next Thursday from noon to 1. And Ariel's going to be doing an interview with Josh LeBaire, which would be very interesting. And we'll also have an interactive component to the conversation next week as well. So looking forward to seeing everybody there. Floor is yours, Ariel.
Great. Okay, thanks, Minnie. So I think Dan is going to turn on his camera so we can see him and introduce our speaker, who we're thrilled to have join us.
So
I should add.
okay.
I should add that I don't know if Dan's going to say this, but this is a long time coming because originally Rebecca was going to visit us last spring, and then COVID hit, and then she was going to visit us at the beginning of last fall, and circumstances intervened to prevent that. So we're thrilled to finally get you here. So Dan, please take it away.
Okay. All right. So this is first colloquium of the spring 2021. So that's very exciting. So those who don't know me, I'm a faculty member at CC. My name is Dan Shim, and I'm a mineral physicist. And I'm honored to introduce my fellow mineral physicists today. It's my pleasure to introduce today's speaker, Professor Rebecca Fischer from Harvard University. So Professor Fischer got her degree from, BA degree from Northwestern University, and got PhD degree from University of Chicago. She worked with Professor Andrew Campbell at University of Chicago. Then she was a NSF postdoc fellow between 2015 and 17 at Smithsonian National Museum of Natural History. And at the same time, she was also affiliated with University of California, Santa Cruz. In 2017, she joined Earth and Planetary Science Department at Harvard University as an assistant professor. She's a compressed distinguished lecturer this year. Compressed stands for Consortium for Materials Property Research in Earth Sciences. So it's basically a premier sort of consortium for mineral physicists. So it's highly regarded lecturership that she has. So today she's going to talk about core formation on Earth and Mars. So Rebecca.
Great. Can everyone see my screen?
Yes.
Yep, looks great.
Well, thank you all for coming, and thanks for that kind introduction. Today I'm going to be talking about core formation on terrestrial planets, and specifically using Earth and Mars as sort of case studies. And the reason why we're doing all of this is that core formation is one of the most important processes that a planet goes through during its formation and early evolution. To first order, core formation is what sets the initial compositions of a planet's mantle and core. So I always like to start with a brief overview of how the terrestrial planets would have formed. So we started out with the disk of dust and gas in orbit around the proto-sun. And these solid dust grains collided with one another and stuck together to form increasingly larger solid bodies. Eventually, we formed the building blocks of the planets, which we refer to as planetesimals or planetary embryos. Those bodies then continue to collide with each other in a series of increasingly large and violent collisions until we formed the 4 terrestrial planets that we see today. Meanwhile, while the planets were accreting, they were simultaneously differentiating. Their metallic cores were separating out from their silicate mantles. Energetic impacts on the surface caused large-scale melting, which led to a partial or global magma ocean on the surface of the planet. And the metal from these impactors reacted with this molten silicate at high pressures and high temperatures in a series of partitioning reactions before it sank down to join the core. And these sort of chemical reactions are then what set the compositions of the core and mantle that we see evidence of today. So this talk is going to be roughly split into 4 parts. I'm going to start with some background about accretion and chemistry that we'll need to know to understand core formation. And then I'll get into a model for core formation in the Earth, specifically looking at trace element patterns in the mantle and the so-called light elements in the core. In the third part, we'll build on that model by adding in the hafnium-tungsten isotopic system, which is a short-lived chronometer. And finally, the last part of the talk, we'll show you some similar results for Mars and how they're similar to Earth and different from Earth. Okay, so why study core formation in the first place? It is a ubiquitous process. We know that it occurred on Mercury, Venus, Earth, and Mars. It occurred on the moon. It occurred on a lot of meteorite parent bodies. Presumably it occurred on exoplanets. And since it's such a widespread process, we want to understand the sort of fundamental mechanisms of how it works and what it affects. And here we use mostly Earth and to a lesser extent Mars as a case study for understanding this general process, because these are the planets that we have the most information about. Things like composition of their mantle, seismic data. But in theory, the kinds of processes we're learning about apply to all of these different bodies. When I say the mechanisms of core formation, I mean things like the timescales over which it occurs, the depth at which the metal and silicate equilibrate within a planet, and the degree to which they equilibrate. Fundamentally, core formation is important because of its effects on planetary composition. Just to highlight an example of that, we know that the Earth's core is mostly made of iron with a little bit of nickel, but that's not all that's in the core. So this figure here is showing density versus pressure over the pressure range of the Earth's core. So we're going from the core mantle boundary on the left to the center of the Earth on the right. This top curve is the density for pure iron at the pressures and temperatures of the Earth's core based on experimental data. And then this bottom curve is PREM, the preliminary reference Earth model. So this is what seismology tells us the density of the Earth's core actually looks like. And you can see that in the outer core, there's about a 10% difference between these two curves. And that's referred to as the density deficit. And most of that 10% is thought to be due to the presence of one or more lighter elements in the core, things like oxygen, silicon, sulfur, carbon, and hydrogen. And these elements would have gotten into the core during the process of core formation. So if we can better understand core formation, we can better constrain the core's composition, which is important to our understanding of the dynamo that's generated in the outer core that gives us the magnetic field. And it also tells us about the thermal structure of the Earth's deep interior, because these elements depress the melting point of iron. And core formation, of course, also then affects the composition of the mantle, which in turn affects its mineralogy and structure and its physical properties. Okay, so how do we go about modeling the core formation process? Let's start at the beginning, which is the accretion of the planets from smaller bodies. we study that process using what's called n-body simulations. So these are simulations where we start with some large number of bodies. So these would be those planetesimals and planetary embryos orbiting around the sun. We allow them to interact gravitationally. They affect each other's orbits. And over time, they'll run into each other and accrete to form larger bodies. So I'm hopefully going to show you a movie of one of these kinds of simulations. This one's from Raymond et al. 2006. So the horizontal axis here is semi-major axis, or distance from the sun. So the sun is over here at 0. The little colored dots are all of our initial bodies that we're going to build the planets out of. And they're color-coded based on where they start out in the solar system, so that you can visualize mixing occurring. So red closer to the sun and blue further away. And then this is Jupiter, the big black circle, and Saturn is off scale. And then the vertical axis is eccentricity. So a measure of how elliptical each body's orbit is. So if it's down near 0, it's orbiting the sun in nearly a perfect circle. It's a very stable orbit. It's not likely to run into anything else. And as you go to a higher value, it's now going in a more elliptical orbit, and it's going to probably run into something because it's crossing the orbits of everything else. Okay, so when I push go, you will see this clock in the upper right start to count up in millions of years, and you'll see everything start flying around. So the first thing that happens is we get these spikes in eccentricity. Those are orbital resonances with Jupiter and Saturn. We start to form a small number of larger bodies with low eccentricity and a large number of smaller bodies with high eccentricity through processes like dynamical friction. If you keep your eye on this one here at 1 AU, that just turned from red to orange and quickly turned green and is now getting bluer. That would be our best Earth analog from this simulation. It's about the right size, it's about the right distance from the sun. And so it started out by accreting material from nearby that was all red initially. And then as time went on, it accreted more and more material from further away and became blue. So that's the kind of like useful information we can extract from these sorts of simulations. And so several years ago now, we ran a whole bunch of simulations of this type, a lot more than had been done previously. Because it turns out that this is a very, very stochastic process, and we wanted to get sort of a wide range of possible outcomes. So one of the things we extract from these simulations is the mass evolution of the planets. So this is the mass of the Earth as a function of time for half of the Earth analogs that we made. And you can see that there's quite a lot of variation to them. You have some that reach nearly their final mass in like 20 million years, and some take 150 million years. And some have fairly smooth growth curves because they're creating mostly smaller bodies. And some have these like really giant impacts where they get a lot of mass all at once. So the idea is that by having so many simulations, we can sort of capture all of these variations. Another thing we get out of it is the provenance of the Earth's building blocks. So this is the mass fraction of the Earth in the end as a function of where it originated in the solar system. And the thick white line is an average over 50 of our simulations. And then the thin colored lines are examples of individual simulations. You can see that some of them very closely track the average, and some of them look nothing like it. And this is why we pull from such a large number of simulations, so that we don't accidentally pull something that's really atypical. And as you saw from that movie, there's also this temporal effect that the feeding zone tends to expand with time. And so for the Earth, that means it accretes more material from further from the sun at later times. Okay, so that's your quick introduction to accretion, and that's the kind of information we need to pull out of those simulations to study core formation. The other big piece of information we need to understand about core formation is the chemistry that's involved. So what kinds of chemical reactions are taking place between the molten metal and the molten silicate at high pressures and temperatures in a planet's interior. And to answer that question, we do experiments using a device called a laser heated diamond anvil cell. So there's a photo of one here in the upper left. Basically, we take a really small sample and we squeeze it between the tips of two diamonds to generate very high pressures. And then while the sample is being held at those pressures, we bring in some infrared lasers and like shine them through the diamond onto the sample to heat it up. So in this study, we did experiments at pressures of 31 to 100 GPa. So for reference, the core mantle boundary is 135 GPa. So we're well into lower mantle pressures. And then while it was at these pressures, we heated it up, temperatures up to 5,700 Kelvin to completely melt the sample. So our samples were mixtures of metal and silicate, like core and mantle analogs, that were doped with small amounts of elements of interest. So in this study, we were particularly looking at nickel, cobalt, vanadium, chromium, silicon, and oxygen. And the idea is that after the experiment, you look to see how much of each of these elements you have in the molten metal versus the molten silicate. And that tells you something about the element's preference for those two phases. And you do that at a bunch of different pressures and temperatures. This is what some of our experiments looked like. After the experiment, we cut a very thin slice through the center of the hotspot using a focused ion beam. And then we looked at them in a transmission electron microscope. So this one on the left is from 57 GPa and 4,400 Kelvin. So this black blob in the middle is the molten metal. And then around it is where the silicate melted. And then outside of that is unmelted silicate. And then on the right is just another experiment with the same kind of morphology, but from 100 GPa and 5,700 K. And at these really extreme pressures and temperatures, we dissolved a huge amount of light element into the iron. We found 9 weight% silicon and 11 weight% oxygen. So a lot more than the Earth's core contains. So that was kind of cool. We seem to have surpassed the average conditions of core formation in our experiments. And an important part of this is that we're doing these experiments at extremely high pressures and temperatures. And we rely heavily on the community of large volume press people who do experiments at more modest pressures and temperatures. And we very frequently sort of combine our data sets with theirs to get a fuller picture of how the element's behavior depends not only on pressure and temperature, but things like oxygen fugacity and composition. Okay, so that's our background information. Accretion simulations give us things like the mass evolution and provenance of the planets, and high pressure temperature experiments tell us about the metal silicate partitioning behavior, or the chemistry of core formation. So now we're gonna take that information and put it into a model of core formation in the Earth. So in the post-processing of the N-body simulations, we assign each initial body a composition. It's basically a CI chondrite enhanced in refractory elements that's been equilibrated at a particular oxygen fugacity. So we have a more reduced bodies closer to the sun and more oxidized bodies farther from the sun. And then we just step through the simulation, and we every time there's an impact, we allow it to undergo high pressure, high temperature metal silicate partitioning. So for this first set of results I'm going to show you, we're assuming full equilibration between the impactor's core and the mantle. And we're doing a calculation at 55% of the Earth's core mantle boundary pressure at the time. So as the Earth is growing, it's getting higher pressures. And it's at the liquidest temperature of the mantle at that pressure. And the oxygen fugacity is evolved self-consistently after Ruby et al. 2011. And so you can calculate what the composition of the metal and silicate melt should be from a system of equations that are just mass balance equations and these experimentally determined partition coefficients that we get from the kinds of experiments I just described. And that lets you solve the composition of the metal and silicate that have equilibrated. And then we put that metal into the core and we mix that silicate into the mantle and we wait for the next impact. And so we just step through the whole simulation like that. And doing it this way, the core and mantle compositions that you get in the end are some kind of integration over a range of pressure temperature conditions. So when the Earth was smaller and it accreted something, the equilibration was at low pressures and temperatures. When it's much bigger, it's at much higher pressures and temperatures. So the model includes these elements so far, plus a few more that aren't even listed there, but I just want to call your attention to the ones we're going to be talking about today. Silicon and oxygen, of course, major elements in the mantle, but also potentially important light elements in the core. Nickel and cobalt are really well-studied trace elements in the mantle. And so we always check to make sure that our model can reproduce the mantle's nickel and cobalt abundances. And that lets us know if the core formation conditions we're using are plausible. And finally, hafnium and tungsten define this short-lived geochronometer that can be used to learn about core formation conditions and timing that we'll get to a little later. So this is an example of what some of our output looks like. So here I'm showing how the silicon and oxygen contents of the core change as the Earth grows. This is for 3 different Earth analogs that formed in our simulations. And I chose these 3 because they're the same mass. So the spread in final composition that you see is due to variations in their accretion history, basically whether they're getting more oxidized or reduced stuff from different parts of the disk. And if you look over all of our simulations, you can make a histogram. And we find that the most likely core compositions for the Earth is to have 1.9 weight% oxygen and 5.5 weight% silicon. More generally, we almost always find both silicon and oxygen going into the Earth's core in pretty significant abundances, and usually more silicon than oxygen. But if we compare this to the core's density deficit of about 10%, you can see we're getting sort of in the right ballpark, but there might be room for like a little bit of other light elements like carbon, sulfur, or hydrogen. So I'm just going to touch briefly on those 3 elements as well. We had a study just come out last year now, I guess, looking at carbon and how it behaves during core formation. So we did this same type of experiment looking at reactions between metallic melt and silicate melt at really high pressures and temperatures, doped with a little bit of carbon to see where it would go. And then we did these fancy nanosims measurements to quantify that. So at low pressures and temperatures, carbon is really siderophile, meaning that it strongly prefers to go into the metal as opposed to the silicate. And what we found in this study is that when you go to really high pressures and temperatures, it doesn't have such a strong tendency to do that anymore. And so when we put our data into a core formation model, we calculated that there should be a maximum of 0.09 to 0.2 weight% carbon in the Earth's core. And that's pretty cool because that's exactly the same number you get based on calculations of volatile element depletions in the Earth, like those from McDonough 2003. That's a pretty low abundance compared to what we were just talking about for silicon and oxygen. But that does 80 to 90% of the Earth's carbon budget being in the core. So it's potentially pretty important in some applications. And then a very similar study was done on sulfur a few years ago by Stewart et al. 2017, and they found very similar results. Again, sulfur is more siderophile at low pressures and temperatures. And when they did these really high PT experiments, they found that that tendency kind of went away. And when they ran their data through a core formation model, they calculated 1 or 2 weight% sulfur in the Earth's core, which again is consistent with the volatile depletion trends in the Earth. But now this is an amount of sulfur that's sort of comparable to the level of silicon and oxygen. So This is going to definitely be something we need to take into account when we're looking at like density, for example. And just like with carbon, this accounts for the vast majority of the Earth's sulfur budget. Hydrogen, I don't even know what to say about hydrogen. It's much more controversial and much less clear what's going on with hydrogen. The experiments are just a lot harder and the analyses are a lot harder, and we don't have much data from very high pressures and temperatures. This is a figure from Klesse et al. 2018 showing hydrogen's preference for metal over silicate at different pressures. And based on their data, they decided that the Earth's core should have about 60 ppm hydrogen in it. But other studies have argued for much more hydrogen. I would say this is still pretty up in the air, and I'm not going to put a number on hydrogen. Okay, so if we sort of put this all together, so we've got 1.9 weight% oxygen, 5.5 weight% silicon, 1 or 2 weight% sulfur, less than 0.2 weight% carbon, possibly trace hydrogen, possibly more. It seems like we're like approximately in the right ballpark in terms of like having enough light elements to match the Earth's core density. So that's pretty cool. Although there's a couple of caveats with that. One is that all of these elements will tend to interact with each other thermodynamically in the metallic melt. And so really to treat this properly, you need to treat all 5 simultaneously, not just pull one from each study. And the other caveat is that it's a non-unique solution. There could be other ways to get there. But this could be some sort of plausible candidate composition to look into anyway. Okay, and now let's turn to the mantle. So we want to make sure that we're matching the Earth's mantle composition. And one of the best ways to do that is to check nickel and cobalt. So these are histograms, again, for our cobalt oxide and nickel oxide abundances in the mantle over all of our simulations. And these shaded rectangles in the back are the observed Earth values. So you can see we're getting a pretty good match. The conditions of our model that gave us these plausible core compositions are matching Earth's mantle trace element abundances. So then we can start to sort of change some of the parameters and see how it affects things. And one of the sort of big ones to play with is the degree of equilibration. So there's this idea that if the Earth accreted something that was large and differentiated, the core of that impactor might have merged with the Earth's core so quickly that it didn't have time to really equilibrate with the silicate around it. Geochemical estimates of the degree of metal equilibration tend to be in the range of 30% to 80%. And in these studies, and in this talk right now, we generally treat this as a constant. It's not a constant. It almost certainly was like widely variable from impact to impact, depending on things like the size of the impactor and the impact angle and velocity. But we just don't know enough yet to really justify that degree of complexity. So you should think of these as sort of like an effective average over a planet's history. Okay, so this was a case of all of the metal equilibrating at 55% of the core mantle boundary pressure. And this was our core composition that we found. If we instead only allow 40% of the metal to equilibrate, but keep everything else the same, our distributions shift to the left and we're not getting as good of a match to the Earth anymore. And we're also getting significantly less silicon and oxygen in the core. What's interesting is that if we keep this 40% equilibration, but just do it at a greater depth, higher pressure and temperature, our histograms shift back to the right and we recover the right composition for the Earth's mantle, and we also get almost the same core composition back. So there's a strong trade-off between the depth of core mantle equilibration and the amounts of both metal and silicate equilibrating. So these are good targets for future studies if you want to understand the core formation process, because it's very difficult to put good constraints on them using methods like this. Okay, so from the core formation modeling of the Earth, you can see that by matching the Earth's mantle composition, we get 5.5 weight% silicon and about 2 weight% oxygen in the core, maybe leaving a little room for some sulfur, carbon, and or hydrogen. There's trade-offs in the depth and degree of core mantle equilibration. Also forgot to mention that mantle and core compositions are most sensitive to these parameters more than any others, as well as sensitive to the accretion history. That sort of randomness of what's being accreted. So these are all things that we should really be targeting in future experimental and numerical studies to put better constraints on those. Okay, so now we're going to take this model of core formation in the Earth and we're going to build on it by adding in hafnium and tungsten isotopes. So first, a quick introduction to the hafnium-tungsten system. 182 hafnium decays to 182 tungsten, and it has a half-life of 9 million years. So this is a system that was there at the beginning of the solar system, but is long since dead. But this half-life of about 9 million years is really useful if you want to study planet formation, because planets tend to form in tens, maybe 100 million years. So it's got the right time scale. The other thing that's really useful about it is that hafnium is lithophile, so it prefers to stay in a planet's mantle, whereas tungsten is moderately siderophile. It prefers to go in the planet's core. And so the core formation process will separate hafnium and tungsten, which lets us make isotopic measurements of this later. So you end up with 182 hafnium in the mantle, because hafnium really likes to be in the mantle. And then over time, that decays into 182 tungsten. So you get this excess of 182 tungsten in the mantle relative to the stable isotopes of tungsten that are all hiding in the core. And this is quantified as a tungsten anomaly. This is the equation. Basically, it's just a measure of how much 182 tungsten you have, normalized to some stable isotope of tungsten, normalized to chondritic in parts per 10,000. So in these units, the Earth has a tungsten anomaly of 1.9. And interestingly, the system is sensitive to both the timing and conditions of core formation. So in the next couple of slides, I'm going to show you a series of cartoons to hopefully help you wrap your head around how that works. Okay, timing of core formation. We're going to look at two different end members. The first is a case of very late core formation. So we start with a slice through our planet that is full of 182 hafnium atoms, that are these little brown circles. So it's undifferentiated. And it sits around for a while, and all of this 182 hafnium decays into 182 tungsten, these little blue circles. And then finally, at some late time, the core forms and separates out from the mantle. Because tungsten is siderophile, it prefers to be in the metal, almost all of the tungsten is going to go into, leave a little bit behind in the mantle. On the other hand, if we consider the case of very early core formation, so again, we start out with undifferentiated body full of 182 hafnium. Now the core forms very early. All of that 182 hafnium goes into the mantle because hafnium is lithophile. And then it sits there and it decays into 182 tungsten. So you can already just sort of see by looking at the final snapshots in these two cases that the timing of core formation is going to produce big differences in the amount of 182 tungsten in the mantle. Specifically, in this case, you end up with in excess of 182 tungsten in the mantle relative to the stable isotopes of tungsten, because those all went into the core back at this second stage. Okay, and then hafnium-tungsten is also sensitive to the conditions of core formation. I'm going to specifically use the example of how much metal equilibration you get. It's that parameter K. So again, we're going to look at two end members. The first is complete re-equilibration, or K equals 1. So physically what this means is when an impactor hits the Earth, if it was differentiated, that impactor's core breaks up into a bunch of, it emulsifies into little droplets that then sort of rain down through a magma ocean. And they're so small that they have plenty of time to equilibrate as they sink. And so they just fully equilibrate. And if we think about what that would do to the tungsten anomaly, so here is a sketch of the tungsten anomaly on the vertical axis. So a higher value means more 182 tungsten in the mantle as a function of time. We have our impactor and our target. Initially, they both go up with time as hafnium decays into tungsten. And then when the impact occurs, in this case, you have all of these little droplets of metal raining down through the Earth's mantle, and they are going to scour out all of that 182 tungsten that you've produced and draw it down into the core. So when the impact happens, the Earth's tungsten anomaly drops. And then after the impact, it continues growing again, but at a slower and slower rate. On the other hand, we could have the case of core merging, or K equals 0. So impactor strikes the Earth, core just plunges straight into the Earth's core without equilibrating with the mantle at all. Here it starts out the same with the impactor and target anomalies growing, but now when the impact occurs, there's no sort of scouring out of the tungsten to bring the anomaly down. Instead, what you get is just a physical mixing of the two mantles. So you just get a mass weighted average. So the anomaly ends up here, and then it goes up slower and slower. So what you can see from this is that equilibration reduces the tungsten anomaly. If you have more equilibration, with each impact, the anomaly drops. Okay, so getting into some of our results for this. So here I'm showing the tungsten anomaly for the Earth. This is a median over all of our simulations for a bunch of different values of K, the amount of metal that equilibrates. This dashed line is the actual Earth's tungsten anomaly. And this is for the case of whole mantle equilibration. And so in our model, if we change K like this without changing anything else, we'll get the wrong answer for the mantle, and we'll end up making something that doesn't look like the Earth. So to get around that, we sort of exploited that trade-off that we found between the degree of equilibration and the depth of equilibration. So as we lowered K, we increased the depth of equilibration. That's what these numbers represent. So that in all of these cases, we're matching the Earth's mantle composition and producing something that, at least in terms of the elemental abundances, looks like the Earth. And you can see our best match to the Earth's tungsten anomaly is for K equals 0.4. And that's encouraging because an earlier study by Nimmo et al. 2010 had used a much simpler model and reached the exact same conclusion. And that would correspond to a depth of equilibration of something like 55% of the core mantle boundary depth. But you can see that there's some kind of range allowed. So these error bars here are two-sided confidence intervals to represent some measure of the spread in tungsten anomalies we get when we look at all these different simulations with all these stochastic variations. So you can't necessarily rule something out that doesn't plot exactly on the line. It depends on the specifics of the accretion history. So then we did the same thing, now but equilibrating with a smaller amount of silicate. So that's these sort of blue-green symbols. Specifically, it's a mass of silicate that's equal to 3 times the impactor silicate mass. And it shifts everything up so that now we get a best match to the Earth's tungsten anomaly with about K equals 0.9. And now in green, this was even less silicate equilibration, equilibrating only with the impactor's silicate, which was about the lowest I could possibly think to try. And you can see at this point, nothing even barely overlaps with the Earth. So we conclude from this that at least on average, equilibration must have taken place with some amount of silicate, like at least 3 times the impactor's mass on average. You can also see from this that in the case of whole mantle in blue, the lowest K you could maybe get away with is about 0.2. That's where our error bar is sort of like just touching the Earth's value. And that's the maximum amount of silicate you can equilibrate with. So there's no getting any lower than that. So we take that as our lower bound on K. And that tells us that the depth of equilibration would be less than 0.65 times the core mantle boundary pressure. And you can see nicely from this figure, as I promised you before, that equilibration reduces the tungsten anomaly, whether it's increasing metal equilibration to the right or increasing silicate equilibration going from green to blue. In both cases, the tungsten anomaly goes down. Okay, and then we can also use this to look at timing. So now I'm showing the tungsten anomaly for every Earth analog we produced in our simulations. This is for the case of whole mantle equilibration and K equals 1. So full metal equilibration. Again, the dashed line is the actual Earth value. And they're plotted by the time of last embryo accretion, which you could think of as the moon forming impact or just some kind of proxy for growth timescale. And in this case, we match the Earth's tungsten anomaly for bodies that had this last embryo accretion at something like 20 to 40 million years. So fairly early on in solar system history. On the other hand, if we look at K equals 0.2, we get a very different picture. We find that we can match the Earth's tungsten anomaly for last embryo accretions at something like 75 to 175 million years. It's quite a wide range and quite different. And this is what it looks like if you fill in all of the intermediate values. So basically, there's a range of K and formation timescales that can all produce the Earth's tungsten anomaly. So if you're trying to use a tungsten anomaly as a measure of time, it should always be interpreted with caution because it is really sensitive to these other factors like the extent of equilibration. There's a study by Jacobson et al. 2014 that argued that based on the late veneer mass on the Earth, that the last embryo accretion event happens at 65 million years or later, which is what's shown by this white arrow. If you believe that, that would give you an upper bound on K of about 0.55, meaning that to the right of this arrow, everything that matches this dashed line is going to be sort of yellow or cooler. And once again, we have this sort of massive trade-off now involving the degree of metal equilibration, the degree of silicate equilibration, the depth of equilibration, and also the formation timescale. But you can say things like later formation times require lower degrees of equilibration. Okay, so from the hafnium-tungsten isotopic system, we find, again, this trade-off. We can say that K probably falls in the range of 0.2 to 0.55, if you believe that upper bound. And that would correspond to a depth of equilibration of about 0.5 to 0.7 times the core mantle boundary. So, fairly deep in the Earth, but not all the way to the core mantle boundary. And we can put a lower bound on the degree of silicate equilibration. So what's cool is that these are tighter constraints that we can place on these parameters than you can using modeling of trace elements or other things that have been used more traditionally. But this all comes with the big caveat, again, that none of these parameters are actually constants when a planet is forming. They would all be varying from impact to impact. So, when we say that K is between 0.2 and 0.55, what we mean is like if you sort of took some kind of mass weighted average over the Earth's growth history, you would get a number like that. Okay, and finally, I will talk a bit about the work we've been doing on Mars. And I will start by pointing out that this is the work of my graduate student, Matt Brennan. So why Mars? Fundamentally, we want to know if core formation mechanisms are the same across terrestrial planets. So we think we have learned something about how core formation works in the Earth. Can we just apply that to all the other terrestrial planets now, or do we have to study them all individually? Mars is a good one to look at because we have the SNC and other meteorites from Mars. People have used these meteorites to estimate the composition of the Martian mantle. And it certainly bears some significant uncertainties, but it does give us some kind of best guess that we can try to reproduce with our model. The other reason why we were excited to study the Martian core is that the InSight mission is currently ongoing. They've placed a seismometer on the surface of Mars, and it is sitting there measuring Marsquakes. And one of the goals of this mission was to try and better constrain the radius of the Martian core. And so I'll touch on this briefly at the very end of the talk, but basically we're doing this core formation model to try and understand the composition of the Martian core, and then turning that into densities, and then core radii, and then seismic observables. So the model we use for Mars is similar to the model I just described for Earth, with a couple of key differences. One is that we are not yet using n-body simulations, although we're working on incorporating those. So for now, we're doing just like a smooth curve that describes the mass evolution of Mars. And that means we can't really do anything interesting with hafnium-tungsten isotopes yet. The other thing that's different about Mars is that it's more volatile rich than the Earth. It has a lot more sulfur in the core, for example. And so all of these calculations become very sensitive to the assumptions you make about volatile content in the building blocks. So what we've done for Mars is we've done a CI chondrite composition enriched in refractory elements by a factor of 1.9. And that is based on an analysis of lithophile volatile elements in Mars from Taylor 2013. But if that is wrong, then everything I'm about to tell you is like slightly off. Okay, so first thing we did was calculate the Martian mantle composition in one of these core formation models. So that's what the white symbols are our calculations of abundances for all these different elements. And then we compared it to some literature studies on the Martian mantle composition as calculated from the SNC meteorites, which are the colored symbols. So generally, we're getting a pretty good match to the major, minor, and trace elements in the Martian mantle. One of the first things that jumped out at us in doing this, Mars has a really high FeO content in its mantle compared to Earth. And that means that when you run this through a core formation model, the building blocks of Mars had to have been more oxidized than the building blocks of Earth. Otherwise, you can't get this high FeO content. Okay, and then we wanted to try and put constraints on some of these sort of aspects of core formation like we did for the Earth. The first one we looked at was the depth of core mantle equilibration. So what we did was we varied the equilibration depth like over the full range of possible values from the surface of Mars to the core mantle boundary, and calculated how the nickel in orange, or cobalt in green, or sulfur in yellow in the mantle would change as we changed that depth. And that produced these curves. So holding everything else in the model fixed, just changing the depth of equilibration. And then we compared these to the studies based on SNC meteorites to see what is like a match to the Martian mantle, which would be these shaded regions here. And then we looked to see where the shaded regions overlap, which would be right here. So this tells us that the average depth of core mantle equilibration on Mars was something like 0.5 to 0.6 times the core mantle boundary. So that's kind of interesting because it's extremely similar to what we found for the Earth in terms of a fractional depth. It's much lower pressures and temperatures because Mars is smaller. And again, that caveat, this depends on what you assume about volatile content, because part of this constraint is coming from sulfur. If you just assume that there's more sulfur or less sulfur, it's going to move this curve around. And then we did the same thing for the degree of metal equilibration, K. Now looking at titanium oxide in blue and sulfur and cobalt. And we varied K from 0 to 1, calculated these curves. These are the abundances that match the Martian mantle based on the SNC meteorites, which tells us that Mars would have had to have a very high degree of metal equilibration to reproduce its mantle composition, a K of something like 0.85 to 1. Recall for Earth, the range we got was 0.2 to 0.55. So that's a pretty big difference, that there's much more equilibration happening in Mars. In terms of the degree of silicate equilibration, it was a very similar story for Mars as it was for the Earth. We were able to put like a really conservative lower bound on it, 20% of the target silicate. It was like fairly comparable, but we couldn't really constrain it further than that. And finally, looking at the core composition. So these are curves of sulfur and oxygen in the core as a function of the oxygen fugacity of the building blocks of Mars. And this is the sort of range of oxygen fugacity that gives you the right FeO content in the mantle. And so that tells us that the Martian core should be made of mostly iron with about 7 weight% nickel, 18 weight% sulfur, 0.3 weight% oxygen, and negligible silicon. Again, with the caveat that there could be a little more or less sulfur depending on what you assume about the volatile content. And so what we've been doing with the rest of this project is then taking these sort of ranges of compositions, turning them into densities, combining that with moment of inertia data to get core radii, and then using those to calculate density and velocity profiles for Mars, collaborating with a seismologist to turn those into travel times and normal mode predictions. So we are hoping that some of this will be useful to the InSight team in terms of figuring out how big and dense the core is and how it might have formed to get that way. Okay, so in conclusion, we started out by looking at accretion simulations and metal silicate partitioning experiments as sort of prerequisites to modeling core formation. In the core formation model, we found strong trade-offs between the depth, timing, and degree of metal silicate equilibration. And the core and mantle compositions were most sensitive to the depth and degree of equilibration and to stochastic variations in accretion history. For the Earth's core, our best guess at the composition is something like 6 weight% silicon and 2 weight% oxygen, leaving room for small amounts of sulfur, carbon, and or hydrogen. For the Martian core, we get 18 weight% sulfur, less than 1 weight% oxygen, and negligible silicon. And these differences are due to two factors. One is very different volatile element abundances between the two planets. Mars just has way more sulfur in it than the Earth does. And the other key difference is the pressures and temperatures of the interior. The Earth is much bigger, and at those higher pressures and temperatures, you get more silicon and oxygen going into the metal. In terms of the process of core formation itself, for the degree of metal equilibration, the range we came up with was 0.2 to 0.55 for the Earth and greater than 0.85 for Mars. So that was kind of an interesting difference between the two, and maybe is telling us something about the types of impacts that these two bodies experienced. In general, we think that giant impacts would have very low degrees of equilibration, and very small impacts would have very high degrees of equilibration. So that could be part of it. Undifferentiated impactors would have the highest degree of equilibration, presumably. So maybe Mars is just made of small and or undifferentiated bodies. For both Earth and Mars, we can rule out very small amount of silicate equilibration, but we can't say much beyond that. It just turns out that the chemistry is not that sensitive to the amount of silicate participating in the equilibration beyond a certain amount. And the depth of equilibration is on the order of 0.5 to 0.7 times the core mantle boundary depth on both Earth and Mars. Interesting that it's similar. It might be suggesting that there is a similar extent of melting or something. And I'd just like to end by acknowledging a whole bunch of collaborators on projects that I presented here and several different funding sources. Thank you.
Great, thank you very much. And let's see, we have some questions coming in. So those who want to ask questions, please type them up in the Q&A. You can also, please don't put them in the chat if you can help it, because those easily get lost. So I prefer that you put them in the Q&A. And if you want to raise your hand, you can also do that. And I'm happy to call on people to speak and open up your mic if you want. And I see, in fact, that Steve Ruff has his hand up. So why don't we start with Steve? Your microphone should be on.
Hi, that was great. So I'm curious about your experimental work, and I didn't quite understand the nature of the starting material that goes into the anvil for heating. Is it just literally elemental material, or is it already silicate and other material that goes in?
So generally in these kinds of experiments, it'll be like some kind of silicate. Sometimes we use like a natural olivine. Sometimes we use like a synthetic pyrolytic glass, but just, something mantle-ish. And then we'll have some kind of iron-rich alloy as the metal. Frequently we make our own alloy so that we can like dope it with really small amounts of trace elements that we want to study.
Okay, so you're just trying to understand, you're assuming a mantle has already formed, and obviously you're trying to then understand how that transitions into a core and mantle separately. Is that right?
Yeah, I guess you could say that.
Okay.
All right. Should we move on? So Lene McCann asks, your model differentiates during each impact. Are there points at which several impactors are being differentiated at once?
Good question. I've never checked. So all of the all of the like differentiation happens in the post-processing of the n-body simulation. So we run the n-body simulation. When it's done, we look at the output and we go, oh, this planet looks most like Earth. So then we take that planet and we basically work backwards to like find out everything that's going to end up getting accreted by that planet, and then like step forward and like do the differentiation. So we don't actually calculate every impact on every planet in the simulation. We're only tracking the ones that are going to end up in the Earth. But it is quite possible, because if the Earth accretes something big, sometimes that body has already accreted things by itself beforehand. So we have to kind of keep track of all of that.
All right. Another question. Joe O'Rourke asks, well, first it says, awesome talk. He asks, could you comment on how your n-body simulations relate to new ideas about planet formation via pebble accretion?
Pebble accretion. Okay, a few things about pebble accretion, I guess. So I've never done any calculations with pebble accretion, and I would love to. But like my intuition is that since they're growing the planets mostly out of pebbles, you would have all of these small bodies. You would have very high degrees of equilibration, I would think, more so than in giant impacts. But the one sort of confounding thing about pebble accretion is that it grows planets very, very fast. So fast that I'm not sure it could ever be reconciled with the hafnium-tungsten isotopes, even with all of these trade-offs you can play around with. But I'm not sure that anyone's actually done that calculation.
Sorry, I was muted. Another question from Ken Yuan. Why is the error bar of the tungsten 182 anomaly so asymmetric, he asks?
Yeah, let me see if I can.
That's one of two questions.
Like
And
those?
we should probably, I guess that's what he's asking about.
So these are all two-sided confidence intervals. I forget what percentage. So they're showing a very skewed distribution. It is easier to produce a super crazy high tungsten anomaly, like if you're like really reduced and form really fast, you can get an anomaly that's like way off the scale. And it's hard to produce an anomaly that's like down by 0. So I think they're all just like skewed distributions.
Just because of the mechanics of what's easier to do. He has a second question. It's just kind of it's a redox question. Could we know how much Fe2O3 is in the Mars mantle? Is that's sort of bouncing off of your stuff, I guess.
I think there are estimates of the amount in the upper mantle, although I can't tell you off the top of my head what that is. But I'm not sure how well we understand like the rest of the mantle.
Okay.
I believe Mars Fe2O3 is lower than Earth's Fe2O3 in the upper mantle,
right.
Which is like super counterintuitive since Mars has more FeO relative to Fe compared to Earth. But I think that's just an upper mantle process.
Great. And one interest of time, I think we should ask one last question and I'll let you go. It's late out there. So oh wait a minute, there's another two more questions just popped in. Well, Tom is actually commenting. Tom Sharp says, I think pebble accretion, to go back to that question, would result in the impacting bodies forming faster and hotter. One might expect the embryos to be more differentiated. How would this affect models for Mars? if their embryos are more differentiated.
Well, Mars, we think, did form pretty fast, so that could be consistent with pebble accretion. And I don't know, if you're forming Mars mostly out of pebbles, it seems like that would be consistent with a high degree of equilibration. I'm not positive if that's what you're asking.
Maybe Tom will follow up. Or Tom, do you want to? I'm going to activate Tom's mic if he wants to. If I can find him here on this long list. Tom, if you want to follow up, I activated your microphone.
Yeah, thanks. That was a great talk. I just wanted to say that, the pebble accretion doesn't necessarily mean that Mars formed by pebbles, but that the whole process is speeded up. You'd still be forming these embryos just much, much faster. But if you form embryos faster, there's a lot more short-lived radionuclides around to heat them. So it would really change how much these building blocks were differentiated. Right, because everything that forms quickly is hotter, gets differentiated.
Yeah. I mean, I guess I think of Mars as an embryo.
Yeah, and we think it formed very quickly too.
Yeah.
Okay.
Interesting.
All right. One last
Where's
question.
Steve Desh?
Oh, go ahead, Tom. Sorry.
You said, where's Steve Desh when you need him?
I was just thinking that. So one last question here, which is a little bit bigger picture. It's from Joe O'Rourke again. So he says, my understanding is that the radio science experiment is now InSight's best hope for determining the radius of the Martian core. So he's wondering if you, and I'll just say you or anyone else, are working on predictions for that measurement. So what's the radius of the Martian core, and it might be verified or refuted.
I have a bonus slide. I never get to use my bonus slides.
I had a feeling somehow that this would be a fun one.
Ooh.
This. So this is the size of the Martian core you get depending on different geophysical and geochemical parameters. So okay, so it's like the amount of sulfur in the core, a thermal boundary layer at the core mantle boundary, the mantle temperature, the delta V of melting in the iron sulfur system, and the crustal thickness also factors into this. This is all for one crustal thickness. So if you could tell me the core size, I could like pinpoint you on one of these figures, or if you could narrow down any of these, that would be helpful. We have an equation that just relates all of these variables.
Right. So there is a game to play there, at least a guessing game. All right. So to flip it around from the question, so once if InSight does get some constraint on the core, you'll get some constraint on some of these other parameters. So that's kind of exciting. All right. Well, thank you very much. That was a lovely talk, and thanks for allowing us to be persistent to get you here finally, even if it's only virtual. And thanks for staying up late on the East Coast. Well, it's not that late, but it's dinner time, so you're probably hungry. So thanks very, very much, and thanks for your patience with the questions. And look forward to seeing you again sometime.
Oh, thank you.
Thank you.